Check, check, hello everyone. Hello, hello, check, check, test, test. Okay, hello everyone. My name is Wisa, and today I would like to explain more in depth about uh, a paper about comparing the efficacy of the first distance, zero Winkler, and Jaccard similarity for prompt injection detection in large language models. So this paper is made for from algorithm strategies course at ITB, and I'm very happy to share that. Yeah, I'm very happy to share my work with all of you. So first of all, what is my paper about? My paper is about, of course, comparing the efficacy between these three algorithms. These three algorithms are part of the fuzzy matching algorithms. So essentially, what fuzzy matching is, instead of exactly matching a string from a specific text to a pattern, we use we create a similarity score and then use a certain threshold to decide whether it is classified as prompt injection or not. That's basically the idea. So we all know that in recent years LLM has always been a big thing, and unfortunately the architecture of LLM itself are prone to a new kind of problem or vulnerabilities that are called prompt injection. This is where people create a prompt which allows them to somehow exploit and get uh, secretive data, or sometimes even compromise the system just from the prompt itself. And so yeah, it is a very dangerous vulnerability, and it is quite uh, dangerous and very important to be handled. And fortunately, a lot of people already handle this. So in most LLMs nowadays, usually they create some sort of a small LLM as a layer of validation to decide whether it includes prompt injections or not. However, I do believe that uh, it is still too heavy. You know, inference itself is not an easy thing to do, and my the idea of my paper is to, let's say, we create a first layer so that the process can be lighter and we can like early detect uh prompt injection instead of like relying too much on the small LLM that is being used to classify itself. Yeah, so that's my background. These are the dangers. And so what are the three algorithms that I'm using right now, and how does it differ from one another? Well, let's start from the very first, which is Levenshtein distance. So Levenshtein distance, the idea is basically you count the number of uh, edit, the number of addition, deletion, or maybe even alternation of characters that is needed for a pattern to become the specific text that we are searching for. So that's difference and distance. So for example, if we have let's say ABC and then ABD, well, the difference and distance score won't be that high since they have like one character different. And when we're talking about the next one, which is zero-Winkler similarity, so this is actually a combination of two algorithms. So we first talk about Jaro. Jaro is uh, some sort of a it's also a similarity score. So Jaro counts basically how many, how do I say it? I think it's yeah, transpositions. How many transpositions are needed to make a certain pattern becomes a certain text. And so basically, let's say we have ABC and CAB, you will realize that in both of these cases, both of these string, they both have the same number of characters and the same kind of characters. But the zero Winkler similarity will not give a full score for the reason that the C that is supposed to be at the end of the first word is on the pattern itself is actually on the first is acts as a first character. So we won't give a full score of zeroing or similarity. That's basically how the algorithm works. And the last one is Jaccard. Jaccard similarity is a lot simpler than the two others. It basically calculates the intersection, sorry, the intersection of a set between the text and a pattern divided by the union of both set. So what does it mean? So for example, we have ignore previous instructions and ignore all instruction. So we both know that the intersection has size. The intersection is 2. The size of the intersection is 2 because they both have ignore and previous, right? Ignore and previous. Sorry, ignore and instructions. Sorry. And the union size is 4 because ignore instructions previous and then you concat it with all basically. So the size will be 4. The the Jaccard score, similarity score, will be 0.5 because basically it's 2 divided by 4. It's that simple. And Jaccard is, yeah, it's very simple compared to the two others. So what is the methodology that I'm using for this paper? So the methodology first is I found a dataset. I used the dataset of DeepSet prompt injections that I took from Hugging Face. They have 662 samples, including 399 of benign queries and 263 injection attacks. Now, when we're talking, okay, and then the environment itself, basically, I use this Python, scikit-learn, matplotlib, and RapidFuzz. RapidFuzz is for the string matching algorithm. And pre-processing, basically just collapsing in single space, consecutive white space, and single space, and blah, 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 and then sliding window. So this is important. So we all know that basically, if you just match a pattern, use the fuzzy matching from a pattern to the whole text, it won't produce a high score. It will only produce a very, very low score instead because of the how different it is. Now, if we instead use the word, it would be impossible because prompt injection itself is not on a character level. They compare literal words, a set of words. Like for example, ignore all previous instruction. That's like 4 words, right? So we have to find a way to, since we cannot chunk it by word, and at the same time we cannot process all of the text as a whole. We have to find a way for the algorithms to be able to find feasible technique so the score can be used to classify it correctly. And what I'm trying to do here is we create a sliding window. So instead of like inputting all of the text or only word by word of the text, we create a chunk from those texts. The chunk itself is basically the sliding window. It extracts chunks from the documents, which word count approximates the pattern length. It's between 2 words, and then compute similarity for the chunk. So it is a lot better. So for example, if a chunk is like ignore previous instruction and so and then the algorithm can basically create a more accurate and representative score of it. And so the sliding window is being used to scan throughout all the text, and then it will return the best, basically. It will return the best score. And then moving on, the evaluation itself will use the standards, F1, accuracy, precision, and all that. And then we can skip to the result. If we see the result here from the F1 score per fault, we can see that the best one is Jaro Winkler, and the second is Levenstein, and the third is Jaccard. So, of course, as I said before, it's normal that Jaccard falsely classify this because Jaeger only matches whether a word is or a set of word is exists or not. And we can see here that Levenstein is less, yeah, well, it's also quite good with the F1 score of 0.7 up to 0.75. It's still not as good as Jaro Winkler. Now, if you ask me why, the reason might be because Jaro Winkler, uh, sorry, I forgot to explain the Winkler part. I've explained Jaro, but I forgot to explain the Winkler part. So the Winkler part is basically extends the Jaro algorithm in such a way so that it rewards, uh, it gives, um, it gives weights to the prefix that has the same characters. This is mainly done because the fact that most typos are being done at the end of the word or at the end of the sentence. And because prompt injection is, as we know, tends to follow a certain prefix pattern, like ignore this instruction, you are now under my command, or please execute this command, like they have a certain prefix that is fixed, like so that is the reason why Jaro Winkler performs the best here, because most of prompt injection, if we see, they use a lot of the same prefixes, and so because of that, the Jaro Winkler can kind of like detect it more easily and more accurate compared to the two others. That's why the Jaro Winkler is the best performing one here. And then, oh yeah, one thing I forgot to mention, we use some sort of training. So it's not actually a training since it's not a machine learning model, but the training here is to tune the threshold. So we tune the threshold in such a way so that since we don't know which threshold is the best to like classify whether one is prompt injection or not, we need to find the soft spot for a threshold so each models can perform best. That's why I do the certified k validation here to basically get, first of all, of course, to the threshold, and second of all, of course, to see whether we're not like overfitting. Sorry, not overfitting. It's not a machine learning model, but it's more like making sure that the data is fair, since maybe there are maybe some data sets that is not, or sorry, or maybe some word dictionary that is not handled in the dictionary of the word itself that is being used for these three algorithms to scan the patterns. And yeah, we will talk about limitation. Of course, the generalizability pattern is really constructed exclusively from the training partition of a single data set. So it's really, sorry, very exclusive, and it's not that general. If we can have a different data set, the result might be different. But of course, the objective of this paper itself is, of course, to analyze the three algorithms. So it's, of course, not production ready. And then second of all, yeah, it's blind to semantic intent. So let's say we have a new semantic intent with a very different lexical structure, then they won't be able to detect it. And of course, the computational cost scales linearly with the the pattern database. This is the more pattern database we have, will probably cover more and be more accurate, but at the same time, it will make the computational cost higher. And finally, we have a future work here. This is my advice. So I think, well, I do think that this is kind of outdated, string matching. I think string matching might still be useful for some application that are very, you know, let's say limited for computational cost. Maybe we can, in a way, replace it with these instead of like a small LLM, because of course it costs a lot less compared to uh, a small LLM. And yeah, from the conclusion, we can conclude that it is it is the result of comparing the efficacy between these three algorithms are quite interesting. And from the nature of the prompt injection itself, we can see that the nature, sorry, the mechanism of each algorithms uh, are shown. Some also algorithms are shown to be better than others due to the nature of the prompt injection itself. Like here, we have Jaro Winkler, who performs best because it rewards prefixes compared to the other. And I think that's all for me. Thank you for listening, and I hope you have a great day. Assalamualaikum warahmatullahi wabarakatuh.